Hello, everyone. Thank you for joining the first of our 4 sessions in our webinar series entitled Bioprocess Workflows That Win. We're excited to share with you today what differentiates Repligen as a solutions provider in the bioprocess market. And over the next 4 weeks, we will journey through the benefits of our impactful technology solutions that we bring to the market. Before we delve into our upstream intensification topic for today, I just want to make a short introduction to Repligen. Here at Repligen, we have a track record of developing, launching, and supporting disruptive technology solutions, having brought 10 solutions to the market since 2017, which has led to a 5-year growth rate in the company of 41%. In general, our technology solutions bring efficiency and productivity gains to biomanufacturing, and we've developed technology leadership in multiple areas. The first is in upstream process intensification with our Excel ATF and CrossFlow TFDF technologies. And then on the downstream processing side, also with Opus prepack columns, affinity ligands and resins, Tangenix flat sheet cassettes, and our hollow fiber modules. Thirdly, with chromatography and TFF systems, which you can see pictured on the bottom of the slide. Fourthly, with at-line and in-line advanced analytics with both Solo VPE and Flow VPX slope spectroscopy technology, and ultimately with total fluid management solutions that enable single-use bioprocessing. Our technology journey has evolved to offering ultimately fully integrated solutions. We've started over the years with differentiated consumables, and then we're able to add standard and custom flow paths that then interface with our differentiated and scalable chromatography and TFF systems that include advanced analytical technology for both process monitoring and control, ultimately rendering a complete integrated technology solution for upstream and downstream biomanufacturing. In addition, our technologies serve many markets, from traditional modalities, including recombinant proteins and vaccines, to new modalities, including cell and gene therapy and cultivated foods. So with this brief background, I'm excited to hand over to Melissa Carpio, our Director of Global Upstream Field Applications, who leads a very talented team who drive the development and implementation of intensified cell culture processes every day. Melissa will speak to us today about our solutions in upstream intensification.
Thank you, Christine. And thank you everyone for joining me today for this webinar. I'll be talking to you about disruptive technologies that are transforming upstream process intensification for all modalities. So the agenda for the talk today is I want to just briefly talk about the drivers for process intensification, and I want to go into two of our upstream technologies that are big players in process intensification, which are the Excel ATF and the CrossFlow TFDF. And at the end, I'd like to touch on what we see as the future of process intensification. So the drivers. So a lot of people always ask me, why do people intensify, or why should I intensify? But honestly, that answer varies from person to person, and that answer comes from you. So what we can tell you is what people have told us. And we see that process intensification drivers fall into 3 buckets. Business, so that then people want better economics, so smaller plant size, of course, to reduce cost. The other one is process. Specifically, most of the time, it's higher productivity. Sometimes, specifically for biosimilars, it's improving product quality. And then also other people are trying to go towards semi-continuous or continuous processing. And for that, you absolutely need intensification. And lastly, and more prevalent that we're seeing is environment. So we get people that have come to us and say, we have a sustainability initiative. And we read that by intensifying your process, one of the side effects of it, or the other benefits that you can get, is actually reduced energy use, reduced waste, reduced reagent, and of course, smaller footprint. So sometimes people come to us and it's one of those. Sometimes it's a number of those. But regardless of your driver, if you choose one, you reap the benefits of all of it. And also the tools and strategies are very similar when you start to want to implement and check the feasibility of process intensification. So Repligen is recognized as a leader in process intensification. And a net promoter score in 2022, industry folks in our industry were asked, who do you view as a leader in upstream intensification? As you can see here, a lot of familiar names, but Repligen comes out as number one. And if you actually look at the right, that's off to the side, it says Refine technology. Repligen acquired Refine in 2014, and Refine actually is where the ATF technology was developed. So as I said before, Repligen has two core upstream intensification tools. One of them is the Excel ATF technology, which has been around for over 20 years, being used initially for unstable proteins for continuous perfusion. But as I'll explain later, the application extension has gone far and wide with this particular product. The second one is a newer one, and it, from our perspective, is a very disruptive technology, specifically in gene therapy, and that's the CrossFlow TFDF. And I'll be going into both of those in much more detail, starting with the ATF. So Excel ATF, so it continues to solve manufacturing challenges, because I said we've been doing this for a long time with this particular technology. It is a cell retention device, and it's the cornerstone for intensification and continuous. What we've heard and what we've also seen with the number of customers that have used it is it increases throughput, productivity, and capacity. We've been able to get reduction in bioreactor size, sometimes up to 10-fold, where a 10,000 liter reactor, when you add either N-1 perfusion and or N perfusion, you can get it down to even 1,000 liters. Flexibility, so a lot of folks are doing this so they can get smaller, more flexible facilities. And then also cost. It does reduce cost overall. Why alternating tangential flow? And we get this a lot. What makes it better? Essentially, most other cell retention technologies connected to the bioreactor are on a continuous loop. Alternating tangential flow is exactly as it sounds. So there's a diaphragm pump, silicone diaphragm at the bottom that acts as a pump. The hollow fiber sits on top. And on the exhaust stroke, we use negative air pressure to pull culture from the reactor through the filter. And then on the pressure stroke, we use positive air to push it back up. While that's happening, we know that there is a backflush action. So the filtration brings the components to the wall, but that backflush action of the back and forth actually releases components from the wall. And the benefit of that is, one, you get higher viable cells because there's not any sticking on the wall and they're happier. And then also the filter longevity. So for very high demand, so high density, and also for longer cultures, we see that ATF performs much better. So like I said, we do have a range of offerings starting at bench scale, going all the way to clinical and commercial manufacturing. The Excel Lab dual controller is able to run ATFs 1, 2, and 4. And then the current version of our controller is C410, and that runs 4, 6, and 10, both non-GMP and GMP. And coming very soon this year is the Excel large scale controller. The pilot version will be able to run ATF 4 and 6, and then the Plus, which is the more large scale commercial manufacturing version, will be able to run ATF 6 and ATF 10. Also, as I mentioned, our devices, so the filters themselves come in 2 device formats, single use and stainless steel. The single use ones come fully assembled, already pre-sterilized, and all it needs to be is connected to the bioreactor and also your harvest or media bags for the permeate. So as I said before, the ATF has broad industry adoption across multiple platforms. So if you look at the graph on the left, we're showing modalities here, molecule types. And we're not able to share a lot of specifics around processes due to confidentiality, but we can aggregate them just because we are active at over 500 sites globally, also large CMOs through North America, South America, Europe, and Asia. So if we look at the molecule types, the most prevalent one is monoclonal antibodies and fusion proteins. And that piece of the pie was a lot bigger. It's getting smaller due to application extensions that we're seeing. So you can see here, we're also using it for recombinant proteins, cell therapies, and more recently, and I'll get into this, is plasmid DNA, so E. coli processes, and cultured meats. So we are always getting requests about, can I intensify this? And we always take a look at, feasibility, technology fit, and that's how come this pie is continuously changing. And then in terms of what it's being used for, so application. So we are in over 40 commercial processes in 9 countries, and a lot of more processes, so over 50 in phase 3 or other late phases, and hundreds that we're aware of that are in early stages. But what it's being used for in those processes also varies. So again, the most prominent piece of the pie is end perfusion. But I can tell you when this first started, that was 100%, because that's how the applications for ATF started. But now you can see the pieces of the pie are changing. So a quarter of our applications are N-1. And then we are also seeing now additional, so some people are doing concentrated fed batch, high productivity harvest, just harvest. So it is changing. And we are seeing, again, pushing the boundaries of what the systems in this can be used for. For reference, the ATF use, we're aware of it being in over 50 articles and presentations across a diverse range of these molecules and cell types. We actually have a memo that collates a list of all of those references along with links. So if that's of interest, please reach out. We're happy to provide that. So as I mentioned, the largest piece of the pie with regard to modality is monoclonal antibody, and there's tons of examples. What we've done here is put together 4 recent examples. So these are all within the last year that we've been able to find and see, and we know, of course, that these are being used in these particular spaces. So first is Genentech. In August of last year, they celebrated the grand opening of a new clinical supply center. And in their press release, as you can see, the ATF here is a part of that, and that allows them to be smaller scale, more modular. BMS has been using ATF for N-1 for a long time and publishing on it. And more recently, their paper was showing how they're coupling N-1 perfusion with PAT to further optimize their process. WuXi has also been one that's been publishing on their use of the ATF since at least 2018. Last year, they had another article talking about the future of bioprocessing, and their focus is on continuous. And you can see in this article image here, the ATF is, again, a prominent part of that. Also, Syngene, just last month, they released an application note on using N-1 intensification with high density N inoculation. And from that, they're able to achieve 3 to 4-fold higher titers for their MABs. And they're calling it their intensified fed batch process. Following MABs, I'd like to get into a couple of case studies on some of our more exciting, not more exciting, but exciting and newer application extensions. So the first is with MSD Animal Health. This is a collaboration we did with them. And there is an application note that has been published. And again, we can share that. The link is also referenced here. And this is for animal health, which historically has been cost prohibitive for ATF. At least that was the feeling. But MSD has been increasing their capacity by adjusting batch size and frequency of batches, and they've hit a limit. So they either needed to do a facility expansion or transfer to other manufacturing sites, but they wanted to see, can we increase our facility productivity and output per batch? And as you can, as is highlighted in this paper, the ATF has helped. It's a 5x improvement in cell density, which also led to a 5x improvement in viral yield. And they're able to implement perfusion in a flexible manner. So either at N-1 seeding stage or their end stage production. And overall, they were able to see that they've reduced their cost of goods and lowered CapEx. So that in itself was able to implement ATF in a space where ATF wasn't normally implemented. So that taught us, and now we're making sure that people are aware that even in lower costs, so biosimilars, animal health, there is a benefit to intensification. In addition, they also mentioned that our single-use options provided them ease of use and possibility for close processing, which was beneficial for their particular needs. So the other one is, again, something that we know has been working from our past experiences with it, but the price parity was never thought of as there to implement intensification, but now it is. So we're seeing an increased ask from us to use ATF for intensification of E. coli processes, initially now specifically for plasmid DNA. So as Christine was mentioning, our technologies are used throughout the workflow, from upstream to downstream. And in this particular case, we know that our downstream technologies are a clear fit for plasmid DNA production, but now we're also seeing our upstream technologies are fit also. So we've had success with this. One customer in Asia and also one customer here in, I'm based in the US. So here in the US, we saw a 2 to 3 increase in cell density and also plasmid yield with XCell ATF. And some of you may ask, is that high enough? Is it worth it to do it? And in some cases it is. And the feedback that we've gotten is that, especially in cases where now with gene therapy, we need, triple transfections, you need 3 plasmids. You don't really need a lot of it. And if you can do a lot more in one batch, it's actually very helpful. And also for our customers who are trying to go fully single use, there's a limitation right now in the size of single-use fermenters. I think 300 to 500 liters, depending on the bioreactor vendor. So by adding ATF to that and being able to get more out of that single-use batch, 2 to 3x increase is actually very beneficial. So we're starting to get an understanding and learning more about this particular application. And another one is in cultured food. So this is something where we have been working with customers on this for almost 3 to 4 years now. And it started out slow, just people from the biotech industry going into the cultivated food industry, knowing the benefits of intensification, but asking the question, again, this is a lower, the price that you could sell cultured food for is much less than biotherapeutics, but the benefits might still be useful. And here we are actually seeing. So we are seeing in some cases 100x increase in productivity. And here productivity doesn't mean drugs because the cells are the product. So it's actually cell mass. It's also, again, 3 to 10% in the increased production overall, improved capacity utilization. And I think just even a couple of weeks ago, this paper was published in Nature Food, where the ATF is being used for production here. And what you can see is in fed batch, the densities that were able to be reached were around 9 to 10 million cells per mil. With ATF, they were able to reach over 100 million cells per mil. So that's a huge increase, and also the potential to get so much more cell mass out of one batch. And this particular application was for biomass to be used in cultured chicken meat. So that covers ATF. I hope I gave you a good technology overview and a flavor of the expansive applications that it can be used for. I'd like to switch gears now and go to our CrossFlow TFDF. So again, this is a newer system for us. It was launched in 2020, but even then, despite being launched in the middle of COVID, and then also just fully understanding, we knew that it was a powerful tool, but again, it was the input from the industry where we started to see where does it really fit, and we've been able to get it to fit in some spaces in CHO clarification, but even more now in gene therapy. So we have over 50 install base of our lab scale systems and 15 of our larger scale process systems. So despite being new, we are seeing increased adoption of this. So it is TFDF. So TF is tangential flow and DF is depth filtration. And I'll go into that in a little bit more detail in the next few slides. But the benefits of the system overall, that it is a closed single-use solution. It has a small footprint compared to what it can be used for. And I'll get into that because in some cases it can be used for multiple process steps. And it's scalable up to 2,000 liters. And our software makes it so that it is walk-away automation. So you can set up what parameters you'd like to do, and it is walk-away. So I wanted to show a visual schematic here of what it looks like and why combining these two filtration techniques is beneficial. So we're all aware of both because they've been around for a while. So tangential flow, this is one where the cells retain within, and then you get your product, but your product doesn't really transmit out. Depth filtration is the opposite. Your product transmission is good, but your cells sometimes get stuck in there. So when you combine them, so you have tangential flow and then also depth filtration, you're able to get high cell densities and increased cell retention, but also good product transmission. So where we're seeing the TFDF technology really be beneficial is in upstream process intensification of viral vectors. So you may think, okay, tangential flow, depth filtration, harvest, but it's not just the harvest step. Where we're seeing it be beneficial is throughout the entire upstream workflow for viral vectors, be it AAV and lentivirus. And the reason for that is because of the combination of the tangential flow and depth filtration, it can be used as a traditional cell retention device, while later on also being able to get transmission of secreted proteins. So what I'll be able to show you here is intensification of N-1, so the seed train, also the end production stage, which in this case is the cell expansion. Sometimes it's the media exchange, and then also perfusion post-transfection. So how it connects to bioreactor is very similar to other cell retention devices. It does need two ports because it is a recirculating loop. So there is a feed comes in, it goes up the filter and then returns to the bioreactor via a retentate line. And then there is a permeate line where you can pull to do the perfusion. So my first example is going to be intensified N-1. And this is available as an application note, and this work was done by our internal R&D team. So what they did was compare a non-intensified batch. So just looking at a typical N grown to 3, 5, 7 million cells per mil, and being able to inoculate that as a typical bioreactor batch. A TFDF intensified seed train, one, you can reduce the number of vessels. Also, you can increase the yield, and that's what we've been able to see. And even with the perfusion, so 1 to 1.5 vessel volumes per day, the total volume of media is actually reduced almost twofold. And the other thing they were able to show with AAV9 production is cells coming from a typical N-1 that's not intensified, and the intensified N-1 has the same cell growth and virus production in both quality and quantity when you're comparing the two. And that's the data that's shown here. Is the control is a non-intensified seed train batch. And then we also have a 3x intensified seed train batch. And you can see here that the genome titer and productivity are the same. And then also the viable cell density of the N reactor is also the same. Another case study that I'm really excited to share, so this is again coming from our internal R&D team, is they were doing TFDF-based perfusion cell culture intensification for both AAV and lentivirus. And in this particular case, they use HDK293 cells along with the XP293 expression medium and a 3-liter single-use bioreactor. They did transfection on day 3. In one case, they did AAV8, and in the other case, they did lentivirus. So the control, the batch process, was seeded at 400,000 cells per mil and transfected at 3 million. For the intensified process, they were using a 30 centimeter squared TFDF module, and they used our controller connected to the bioreactor. In the cell expansion stage, they started perfusion 24 to 48 hours after inoculation at 1 to 1.5 vessel volumes per day. And in this case, they were able to get both the lentivirus and the AAV to around 9 million cells per mil, and that's when they transfected. Post-transfection, so they did the transfection, they waited a few hours to let the transfection happen, and then they turned on the perfusion again post-transfection at 1.5 VVD for the AAV8 and at 1 VVD for the lentivirus. And they did continuous harvest from that. For the lentivirus harvest in particular, they stored that at 4 degrees C. And when we look at the results, it's very compelling for a number of reasons. So for the AAV8, let's focus there first. Again, The control batch was transfected at 3 million, and the intensified batch was transfected at 9 million. So we see a 3x increase in VCD at transfection. So you would expect, okay, we should get 3x increase in virus productivity. We actually saw a 9x increase in virus production. And when you look at the cell specific, because we had 3x more cells, we saw a 3x increase in the cell specific virus productivity. So the cells themselves were producing 3 times more. And you ask yourself why, and we're still asking ourselves why. We think, I think personally that the perfusion post-transfection is allowing the cells to be happier. And that's not a thought. You can actually see that here, is that the viability of the intensified cells is much higher than the viability of the control. And because of the continuous perfusion, you're able to take out some of the waste and then also bring in some fresh media. So the cells are happier. And that could contribute to the multiplicative effect that we're seeing, where we get a 3x increase in density, but we're getting a 9x increase in productivity. For lentivirus, it's even more compelling. So we had a 3x increase in VCD here, same thing. Control was transfected at 3, the intensified was transfected at 9, but we saw an 80x increase in lentivirus production, which means that the cells themselves, each specific cell, was producing 30 times more than the control. And you think to yourself, is that consistent, or is that, a one-off? And I wanted to share next some collaboration results we have, one again for AAV and one for lentivirus. So for AAV, we see the same 3x improvement in the AAV production. So we are seeing consistently, 3 to 9x improvement. But for lentivirus, again, in the hands of our collaborator, we saw 80x in our hands. In this particular case, they saw 70x. So this huge improvement we're seeing for lentivirus, we're seeing it consistently. And very specifically, since lentivirus is secreted, we're seeing very good virus transmission, greater than 90%. So we are doing a lot more work in this. And as I said, this is still in the early days of really, truly understanding the power of this technology. But even in our early collaborations and in our own work, it's looking very promising. And I think in the coming months to years, it will only get better and we will only learn more. So I hope that I've been able to show you a good overview of our TFDF technology and the potential that it has with gene therapy applications. And looking forward to the future, I hope I wasn't misleading in thinking that I was going to tell you what I think we're going to be doing with regards to new applications or what new modalities. But really, the answer is both of us, you and Repligen, because where we've seen success in the changing of the pie charts to get new applications, new modalities, it really comes with the industry, with you challenging us and us guiding you to success. So it is a partnership. And I'm extremely proud to be part of the applications team that is driving this in the field. So what we call it guided implementation, and what it is we get a question. I have this pain point, or I'm working on this new process I've intensified before, or I've read that intensification may help. We have a conversation. We learn about your process. We teach you about our technologies, and together we decide, okay, theoretically this works. Technology-wise, this should work. Let's try it. So we evaluate. So we do on-site evaluations, we do a demonstration, training, and we do, sometimes in one run, we're able to get a really good proof of concept. And then we go forward with, you purchasing a system, and we continuing to work with you on the optimization and then the scale up. And it doesn't stop there. Sometimes within one company, we've grown multiple, TFDF, ATF and TFDF, because now they're doing gene therapy. So the future, I think, is endless. If you asked me 5 years ago if I thought we would be using ATF for cultured food, I would have laughed. But now I think it's needed. And same thing as I said for the examples of animal health and also plasmid DNA, where in the past it didn't make sense, now it might. And in very emerging fields like gene therapy, we're seeing great benefits. And that's because of this partnership. And that's really where I see the future is this continued working relationship where you challenge us, and we continue to innovate to meet the needs of the industry. Um, so that's my future looking thought and statement, and I'm excited for it. So in conclusion, as I said before, Repligen is the leader in upstream process identification. We have two disruptive cell retention devices that are used in a variety of different spaces. So our ATF technology, monoclonal antibodies, recombinant proteins, cell therapies, now plasmid DNA and cultured meats, our TFDF technologies, viral vectors. So we've seen success, as I showed, lentivirus, AAV. We have ongoing work and already known success in oncolytic, retrovirus, adenovirus, exosomes as well. We have a couple of customers in exosomes that are seeing, again, really good transmission through the filter. And then also we have customers that have scaled up already to the hundreds of liters successfully with the TFDF technology. And another emerging field, again, we were being challenged, is, sometimes the cell therapies in particular are on microcarriers, or even some of the cultured meats are on microcarriers. And we're starting to investigate, can the TFDF be used for that? And we are seeing early success. So, we have 15 years, more than 15 years in process intensification experience through the ATF and now with the ATF and TFDF. We continue to innovate our technologies to continue to be the fit for upstream manufacturing processes in general. We are scalable from benchtop all the way through to manufacturing. It's proven in the ATF, and we're starting to already show that in the pilot scale in TFDF. And we continue to try to meet the industry needs. And we always value feedback. I always enjoy visiting our prospective and also our existing customers to understand, where we can continue to improve. And of course, dedication to quality. So with that, I end my talk. I thank you for your attention. And we would like to open the floor for a question and answer session.
Thank you, Melissa, for the very insightful perspectives on solutions for upstream intensification solutions for both traditional and new modalities. So we're going to transition now to an open Q&A session. We've seen some very insightful questions as well coming from the audience. So we're going to invite Melissa back in and work our way through the questions from the attendees. Hi, Melissa.
Hey, Christine.
Great. So to start off, one of the questions here is about the CrossFlow TFDF system, and the question is, does the TFDF system run in unidirectional flow and with a depth filter? Customers just looking to understand a little bit more about the physical setup, right? What's the depth filter? How does it function in the TFDF system?
Absolutely. So it is a unidirectional flow, so it is a loop. And so you would need two ports onto the bioreactor. And then where the depth filter is actually the filter in the flow path. So the tangential flow portion is the recirculating loop. And then you can pull the permeate through, and then it's that thicker lumen that's 2 to 5 micron that acts as the depth filtration.
Excellent, thank you. And then another question related to the TFDF system. Is it just for perfusion applications?
Yep, so the TFDF, it is not just for perfusion, but I mean, the mechanism in general is perfusion. So it can, and as I said, I showed in my examples, it can be used for perfusion in a number of upstream process steps. So for example, it can be used for cell expansion. It can be used for media or buffer exchange. It can be used for perfusion post, say, transfection or infection. And then depending on the type of molecule being expressed, it could also potentially be used for harvest. So examples are the lentivirus or secreted AAV. So it is, yes, it's for perfusion, but it's also very versatile with regards to the process steps that can be used.
Exactly. So related, can the same TFDF filter be used for multiple steps, such as cell expansion and viral harvest?
That is correct, yes.
Exactly. Thank you. Okay, and then when we're thinking about connectivity, right? What type of cell culture bioreactors can be intensified with either ATF or TFDF? Is there a preferred bioreactor type for either of those technologies?
No, I know it's actually bioreactor agnostic, both the ATF and TFDF. So the ATF device and the TFDF flow path, they are, you can use any reactor. So all we would do is understand which reactor you have, and most of us have already worked with almost all vendors out there, both multi-use and single-use. And if it's for whatever reason one we have not seen, what we typically do is ask for a schematic of the head plate, so we understand the number of ports that are there. We have a variety of different head plate fittings that we can provide, so we can make sure that we can properly connect. We haven't really run into a bioreactor that we haven't been able to connect to.
And maybe just a quick comment on stainless steel versus single-use bioreactors.
Oh, yep, both. So from the benchtop, you
Right.
can use a glass or a single-use benchtop reactor, and then on the larger scales, stainless steel and single-use as well.
Thank you very much. Okay, so when we're thinking about producing viral vectors, AAV or lenti perhaps, right?
Mm-hmm.
Is there data, that indicates whether TFDF technology or ATF technology might be better suited for those applications?
Yeah, so again, it depends on the process step in terms of complete versatility, because the ATF sizes that are available are 50 kD, 0.2, and 0.5 micron. The larger biomolecules can't be used for harvest in that case. So if you do have a lentivirus or a secreted AAV, those we have shown in the examples that we have that those do go through the TFDF filter. So in terms of versatility, you could use the TFDF technology for multiple steps. It's that hopefully that answered the question.
Yeah, definitely. I think with respect to the recovery, right, because of the larger porosity of the TFDF filter with the large biomolecules, such as an AAV or lentiviral vector, you'll have better recovery in that harvest step that Melissa was referencing. Excellent. So a quick question here, whether either technology, ATF or TFDF, have been used with microcarrier cultures, so non-suspension,
Yeah.
but yep.
Yeah, it's a very relevant question. We actually have a couple of active collaborations right now testing this. Theoretically, the system should be able to do this, but we're trying to, again, have collaborations to show this. As of right now, we have seen success on the TFDF front with microcarriers. What we want to do is get a more versatile set of microcarriers, a more versatile set of cell lines before we can definitively say absolutely yes. So if you are interested in this, to whoever asked the question, we are actively looking for collaborations in this particular space. But those are active right now, and we are seeing preliminary success.
Excellent. And just a quick question here regarding scalability, right? So thinking about both technologies, right? Are they just for development, process development use, or the technologies be used for manufacturing scale as well?
Oh, both. And the idea here is that both systems, we would like to develop in the beginning a process, optimize it, and then scale it up. So for the ATF, as I mentioned, it is already in more than 40 commercial processes. People always ask what size, typically in the thousands of liters for the manufacturing scale. And then for TFDF, since it's a newer technology for us, we have scaled up to the pilot. So hundreds of liters for perfusion. And I think that eventually those will move through the clinic. But absolutely, it's not just for for development. Both systems scale up to manufacturing.
Thank you. Okay, there's a question here about a bacterial application, right? So for intensification of E. coli applications, could
Yeah.
you comment on the membrane pore size and the technology that's needed to think about the intensification of E. coli applications, and could the ATF technology work with lactic acid producing bacteria?
Sure. Yeah. No, again, this is similar to the microcarrier question, an area that in the past we've known has worked with ATF, but more recently, specifically around the plasmid DNA example I have, but more and more over the last couple of months, we've also been getting questions again about other things being produced in bacteria. So to answer the first part of that, the membrane pore size that we've seen success with thus far is the regular 0.2 micron. And then with regards to fouling, we haven't really seen any bacterial processes, as most people know, are a lot shorter. So even with the high demand on the filter, they do last the typical, 48, 72 hours. And in some cases, we've been, investigating, can it go a little bit longer than that? So it's the standard ATF devices that have been used. And then with regards to anything really that's being produced to the bacteria, if they can go through the membrane. So lactic acid, of course, will go through the 0.2 micron. I don't see why that wouldn't work.
Thank you. Okay, and then the next question relates to maybe some better understanding of the hardware, right? The control system and the consumable. So the question is, can CrossFlow TFDF be connected to a C410 controller, which is the controller for process scale ATF applications?
So good question. And obviously that's someone familiar with our devices. So no, so each of those two, so the ATF devices come with their controllers. So for the ATF on the small scale, it's the Excel Lab. And then for the larger scale, currently it's the C410. And as I alluded to in the presentation, this year we'll be launching the next generation large scale controller, which is the Excel LS, which is large scale. So those specifically go to the ATF. And the reason for that is the mechanism of the perfusion is different. So for the ATF, it's the alternating tangential flow. So that controller will work with that diaphragm pump and push up and down. For the TFDF, it does come with its own hardware. So the TFDF lab for the small scale, and then the KTFDF for the pilot scale, and then the more manufacturing commercial scale. So each of the two filters come with their own controllers.
Thank you. In your presentation, you talked about an application called High Productivity Harvest. Could you give us an overview of what that application is?
Yeah, so a High Productivity Harvest, which we call HPH, it's a way similar to N-1 to apply perfusion to your fed batch process. So the way this typically works is post-inoculation, you're going to let your fed batch process go. Again, it depends on the process, but say 7 to 9 days. And then around that time, we would turn on perfusion. And what that will do is one of two things. One is it can extend the duration with which you can harvest, potentially giving you 2 to 3x more. Or the other benefit is that you will get the amount of protein you need sooner. So you could reduce your batch time. But it's still considered fed batch because it is still within that batch. So it's not the continuous perfusion that we were talking about, but it is a way to intensify your process. Again, either to get more or to reduce time.
Thank you. So thinking about implementing an intensification, right? So whether we're looking to intensify a traditional N fed batch process with an N-1 application, or truly developing an intensified N stage perfusion process, how long does it typically take to develop and implement an intensified process?
That's a good question. So I think one, it depends on the definition of implementation, but let's just say that's to get it all the way through scale up, even to say pilot. Um, so what we've typically seen, and again, it varies from process to process, but a typical CHO MAB process that's currently in FedBatch, um, to do both the proof of concept for either the N-1 step or even the N step would likely take 1 to 2 experiments just to show whatever your criteria for success is. So if it's increased titer, or oh, can I reduce my batch time, or for N-1, can I get the N-1 high enough to do a high density inoculation? That proof of concept typically takes, say, 1 to 2 experiments. So that's 1 to 2 months. After that, if after the proof of concept, those results are already fine, you could scale up from there and be in pilot within, 4 to 6 months. If there's further optimization, so say you want to, optimize now the feeding strategy because the densities are higher to get even more intensified cultures, then sometimes people do development. So I would say on average 6 months to a year to implement it into large scale, but it does vary, again, depending on someone's timeline, their ultimate goals, and eventually what they want to achieve.
Really great. I just want to thank the audience for that engagement. Really insightful questions there, and thank you, Melissa, for addressing them. So we also have a short poll that's running. Thank you, Melissa. So we have a short poll that's running in the polls tab. Would really appreciate, again, your valuable input regarding the type of work and what modalities you think are interesting to be assessing or thinking about intensifying with. So that poll is running in the poll tab. And again, today was our first webinar in the Bioprocess Workflows That Win series. We have additional webinars coming up, one per week in the month of February. I think we have a slide that speaks to the content that's coming up. So we're going to be focused on advanced analytics, inline spectroscopy for process monitoring and process control in TFF. We're going to be speaking about fluid management solutions across the entire bioprocess workflow, and ultimately about the solutions that Repligen brings to the market for mRNA and other new modalities. So with that, I want to thank you for your time today. We hope to see you in the continued series of our webinar, and appreciate your time. Thank you.